and by deconvolution application to barcode decoding.
Thank you very much, Ricardo and Tomei. Yesterday I was here in Buzeiro talking about, he was wondering whether he was doing here. More than him, I don't know as well what I'm doing here. I know Tomei is a big friend for I don't know how many decades, but I was not his student and we never worked together. But anyway, I admire his work. I got to know Tomei because of his lectures in Senamac and other Brazilian conferences. And I always got the impression that he was a very good speaker and I wanted to be like him when I grow up. Anyway, and he gave me some good advice during this iteration process. And he said that if I had beautiful pictures, I should not live to the end of the talk or the mini course to show the pictures. This is something that I want to follow today. So let's go to the business of this afternoon. I'm going to talk about a kind of methods for solving a very important, of course I have to say that it's important, mathematical problem that has several different applications, and I'm going to show them to you very briefly. Oh, of course, I'm using my laptop. It will never work. So this is the outline of the talk. What is this very important problem? This is a semi-blind deconvolution problem. And in particular, modeling the coding of linear barcodes. So today, during lunchtime, André gave me another very important advice. You should sell the stuff you do in a way that you can involve people in your work and in the importance of what you're doing. So what are linear barcodes? I'm coming very soon to this point here. Probably most of you have visited the supermarket and you have something with you and you have to go to the barcode reader and you have to do something like a dance in order to get the barcode decoded by the device. And this is a mathematical problem, a very simple mathematical problem. And we are going to use this fancy looking method, the Piecewise Constant Level Set method, in order to solve this problem. So most of the week we are hearing about partial differential equations and applications to partial differential equations. And this is not a partial PDE, this is an integral equation, a very simple one. Simple to state, but not simple to solve. On Tuesday, I heard about Fredholm equations of first and second kind, and the interest was in solving second type Fredholm equations, which are well posed. If you go to the first kind Fredholm equations, then you get to face the problem of ill-posedness in your system or in your integral equation. And that's what we find here, with a bit more complications that I'm going to describe soon. So the starting point of the approach that I'm going to present today is old for me. I did not invent this method, it existed already, and I learned it from this collaborator here, Shusheng Tai, from Singapore. And he brought this thing that they use, this machinery that they use to solve image analysis problems. And we try to do some mathematical analysis for this method from the point of view of inverse problems. So I'm also coming to this point soon. In principle, the piecewise constant level set, ansatz or approach or whatever, it's something that it's an ansatz that you do on the solution of your problem, and it depends on the problem type that you have in your hands. It can be a PDE, it can be an integral equation, an algebraic equation. It's something that reduces the number of degrees of freedom in your parameter space in such a way that it becomes simpler to find a solution under this special assumption. Once you have a problem that fits the setup of this approach. And the barcode problem you do have, in the barcode, you have to find a solution for a problem. The solution is the barcode itself. And the barcode is a function that is piecewise constant. It's either 0 or 1, or level 1 and level 2. And this fits the framework of the piecewise constant level set approach. So this is something that we learned from Tai. Adriano is a former student of mine that nowadays knows much more about this stuff than myself. And he continued working on that. And very recently, we used this machinery here to attack this barcode problem. One of my personal motivations was the frustration to get the barcode read when I go to the supermarket. And this is something that I'm sure I share with many of you. And the one of the results of our investigations is a method or an algorithm that tries to find approximate solutions to this problem. So, what are level set methods or level set approaches for solving a problem? Notice that I'm talking about a special level set argument here. This is the piecewise constant level set. This is a particular form of level set methods. So since you gave me 1 hour to talk about, or 50 minutes to talk about this problem, I'm going to start talking about level sets so that soon it will be more clear what the piecewise constant level set is. So here I have a problem. And this problem does not relate to barcodes or whatever. It is something very similar, which you are familiar to. Let's think about a PDE. So this is a very simple PDE. You have minus or plus from U equal to X. This should hold in omega. And you know that U is equal to 0 on the boundary of omega. Omega is a square, for instance, or a cube. And you have an operator here that maps X to the solution of this problem. Actually, to the Neumann trace of the solution, at the boundary of omega. Okay? So you give some force and term here in this PDE, and you compute the solution, and you measure the solution at the boundary, and you want to solve a solution you see that this abstract framework here describes, in this case, it is a very simple linear problem, elliptic problem. The problem, if you know X, the problem is well posed, but the problem is given U, compute X. This is the unbounded problem, okay? And most of problems of interest related to PDEs, they concern determination of unknown coefficients in the PDE, okay? There's another problem that we use it to attack. It's Laplacian from U plus Cu equal to something, okay? Then you want to determine X at C, or you want to determine both, C and X. And the special assumption that we are going to make is that the coefficient to be determined is a piecewise constant function that can assume 2 or 3 or a finite number of constant values, okay? And this was bad. So some fitness is involved in the talk, as I can see. This is the exact solution of the problem. Okay. This is the X. And I solved the elliptic equation with this right-hand side here. Okay, and I computed the solution, and the trace of the solution at the boundary is the data to my problem, to my inverse problem. And this is the data. This is the Neumann trace of the solution at the boundary. See, we had 64 finite element nodes at each boundary of our square. And here we not only computed the solution, but we also added some noise. I think the level of noise here is something like 10% or so. And here it comes. This is the initial guess for X. And the method that we study does the following. It computes an evolution based on a gradient type method that changes the shape of the unknown function, the unknown coefficient, in such a way that it approximates the desired coefficient to be identified. Okay? So I think I can make it bigger. Yes, I can. Okay. And there is, this is it for this problem. Okay. What is behind this evolution here and what are we seeing here? So in principle, if you write your problem like this, you have no guess what x can be. X could be anything, okay, L2 function. But we make the assumption this is the level set. Ansatz. You say that x is a projection of a smooth function. Okay? And this projection is an approximation to the heaviside projection. Okay? So, you know the problem already? So this h is something that works like this. And this is epsilon. This here is h of t. So phi is a smooth function, okay? And the projection of phi, or h epsilon of phi, is something that becomes either 0 or 1 in this case. So we know the levels of the unknown coefficient, and we rewrite our original problem in this way, such a way that now we have to solve it's like this. Okay? What is the advantage? Because when I had the previous formulation, f from x equal to y, or y delta, the space of piecewise constant functions is not a linear space. I add two piecewise constant functions, and the result must not be a piecewise constant function. So this is bad to do variational calculus. Once I write this projection here, now I work on the space of smooth functions, and things becomes easier to compute. I can compute a gradient and can compute a variation in this setting here. That's why level set methods are interesting. And how do x and phi relate? So you remember the coefficient that I had to reconstruct? It was something like, I don't know, like here, an inclusion here, 1 here, and 0 outside. So if I want to represent this with a level set function, I can simply take, where's my favorite color? It's hidden here. I can take a function, okay, such that here phi is positive. Oh, here it's negative. And here phi is positive. Okay? And when I take h from phi, I get again the characteristic function of this inclusion here. And that's what we saw. We wrote a problem for this new setup. We wrote a minimization problem for this new setup. Of course, in order to include regularization, we had to add some terms in the penalization, once again. But what you get at the end of the day is the evolution that I just showed to you. This is the classical level set methods. They were developed to, here, this is the example that I just showed. They were developed to analyze wavefront propagation in the solutions of PDEs. They were very successful for solving this kind of problems. This is again another setup of the same problem, but now a bit more complicated. The solution looks like a bit more complicated. This is again the initial guess. And this is the evolution of the level set strategy, the same thing that we saw before. Okay? And once again, what we measure our data is just the trace of the solution of the PDE on the boundary. And based on that, we are able to identify the coefficient inside the domain. And some things that we can observe is that the coefficient, the parts of the coefficient that are closer to the boundary, they are simpler, they are easier to identify or to reconstruct than the ones that are hidden inside the domain. Okay? And once again, we don't need to have a simple setup as this one. We can have a more complicated one, for instance, if you have multiple levels. you have something like this, for instance. Okay, now I have a coefficient with two distinct levels, 1, 2, and 0. This is the right-hand side of the PDE. So this is the initial guess. Now I have two level set functions that evolve accordingly to the same strategy, a gradient method, basically. This is the solution of the PDE for the direct problem. So you see that you use here homogeneous Dirichlet condition. And this is the unknown coefficient, the position of the unknown coefficient. We have an inclusion with one value here, with other value here. And this is the evolution of the level set method. So these things are known for parameter identification in inverse problems since 2000, more or less. That's when, for the first time, these methods were used for the purpose of parameter identification, not only in PDEs, but also in image analysis. Okay, so our idea is to use a variation of this method here, the piecewise constant variation, in order to solve a problem where, okay, so much for the pictures, for the beautiful pictures. So that's to keep the audience awake in the beginning of the talk. And then we tried to change this formalismus of level set type solutions using a different setup, using this piecewise constant setup here. Okay. So what is the problem that we want to attack? The problem is the barcode identification. Okay. What is a barcode at the end of the day? Barcode is an image that is black and white, and it has a meaning. It's a sequence of black bars and white bars. And if you have a linear barcode, it's one-dimensional. If you have a 2D barcode, you are familiar to the QR codes, for instance, that we have to scan in our cell phones to pay bills, for instance. And hidden in this visual code is some information, okay? For instance, how much you have to pay for that particular merchandise. And we have nowadays several different barcode symbologies. This I learned while studying this problem. You have, for instance, the ISBN. Probably most of you have a book by yourselves. When you take a book and take a look at the ISBN number, that is also a barcode. And this is a special code that only serves for this purpose. You have mail codes. You have IATA, that is for the air companies, UPC. And these are all linear type codes. For the 2D codes, you have also a huge range of hundreds of different codes, okay? Some codes include only digits, some codes include digits and other symbols and letters, for instance, okay? And there is a very nice site where you can see a huge list of codes with characteristics of all these different codes, depending on the purpose that they were created for. In here, you have some examples. This is an ISBN code. This one I do not know. This is a QR code. You recognize by these three black dots here. But if you look carefully, once you have a barcode in your hand, you see that they are different. They don't follow the same pattern, and they have different meanings. So all these pictures were obtained in this site that I just mentioned to you in the previous slide. Okay. So barcodes are very important. If you go to Amazon, that have to scan and identify hundreds of millions of gadgets, boxes, depending on their codes. It has to do in a very fast way, in a very precise way. For instance, inventory management, retail sales, ticketing, and so on and so forth. Nowadays, when you go to the movies, you have to buy a ticket online and you get one of these codes to be read. And usually this is done in a very large scale, so you have to do it fast, and you cannot allow errors during the decoding of this information. Once you get the sequence of black and white bars, you get basically a number, and this number has a meaning depending on the purpose that you're using the barcode for. Okay. And barcodes are also simple, efficient to be used for this purpose because they can be easily identified. You need only a light detector, a laser beam like this one, but The difference from this to a barcode reader is that it has a source of light, and it has also a detector that can recognize what is reflected from the reading process. And what happens is what is presented here. So here you have the barcode, here you have the scanner. The scanner looks like this, more or less. And it illuminates the surface of the barcode, where the barcode is printed. And then you see that the laser beam is projected and then it's reflected. And when it's reflected, it goes back inside this gadget here. And there is a sensor, and this sensor transmits, transforms the reflected laser in an electric signal, okay? And then you see how does the signal look like. When you have a white bar here, it means you have you have high reflection. And you have a black part, then you have little reflection. And then your electric signal, it's higher when you have the white parts, and it's smaller when you have the black parts. But it's smooth, this is the point, while the barcode is not smooth. And here it's not really a identification of the barcode, so it's not that simple. If it were that simple, the problem of decoding the barcode would be very simple. But the thing is, we are on slide 7. The thing is, in reality, we have something like this, okay? So this is the barcode, and what your sensor gets is this. Or if you look like a function, you see, for instance, here you have 3 black lines close to each other, white lines close to each other. So you don't have 3 small hills here in your absorption. You have something very smooth. And here you cannot, by looking at it, you cannot say whether you have here 1 or 2 or 3 bars, or maybe 1 big bar, okay, here in the middle. So our problem is taking this signal here, this electric signal, and transforming it back into the original barcode, okay? As I mentioned in the beginning of the talk, the mathematical model is very simple to present, not to solve, but to present it is. We assume that the barcode is represented by a piecewise constant function, that the domain where the barcode lives, an interval, 0, 1, for instance, this interval is divided in 2 subsets, or 2 subdomains, D1 and D2, in such a way that in the first domain, the barcode, the function representing the barcode is 0, and in the second one, the function is 1, okay? And because of the nature of the physical problem, we can neglect non-local effects, which is very good for our mathematical model. So the laser beam has a variable intensity profile and with finite width. Thus, the voltage readings of the barcode by the scanner, they suffer non-local effects. What helps us in this situation is that the whole situation is finite. The interval where the barcode is located is finite, and the black bars are finite. So we can, at the end of the day, neglect the non-local effects far from the barcode location. In principle, we know the barcode location, we know omega, and they do not influence the scanning process. Because of that, we can represent the blurring that happens during the barcode process by a linear operator. Not really a linear operator. Yeah, I will come to this point right now. Let's assume we have a blurring kernel here, K. K is an exponential kernel. And you see that it depends on 2 constants here. The first constant is gamma. This gamma is not that bad. We don't know gamma and we don't know sigma, the 2 constants. So gamma relates to the amplitude of the Gaussian kernel. And this has to do with the hardware, with the device itself. So basically, although you do not know gamma, you have a very good approximation for it. So maybe you have tried to use a barcode reader under broad daylight, okay? So when I go for swimming in my club, we have to enter, in order to enter the swimming pool, you have to put your card in a barcode reader. And if it's very shiny, if I go midday for a swim, then I have a hard time passing through the control, because the barcode reader does not work under different assumptions than the lab assumptions, that they control gamma, basically. So if the sun is shining very strongly, then gamma is different and the whole process does not work anymore. The second constant, this is the important constant. And this one, we must assume we don't know sigma. What is sigma? Sigma is exactly what you have to fight against when you go with your card or whatever close to the barcode reader and you try to get it read by the reader. Because sigma relates to the distance. Sigma here is the variance. Sigma square is the variance in this model. And it relates to the sigma between the device and the barcode. So the blurring process is stronger if you are far away from the gadget. Once you get usually you have the barcode in your hand and the reader is over there. So when you get with the barcode closer to the reader, then you reach the prescribed sigma, and then your card can be read. Okay. So this is the problem that we have in principle. This is the convolution kernel, and you know that we have a very good ansatz for the kernel, for this constant, but not for this one. This one has to be determined as well. And the whole process, the whole mathematical model for the scanning process is described by the convolution between the unknown kernel or partially known kernel and the completely unknown function u that represents the barcode. Okay? And we assume the barcode u to be an L1 function and L infinity as well. And a piecewise L1 function, more than this. No? And we assume that the blurring process is described by this. And the mathematical problem that we want to solve is this. Y is equal to k convoluted with u. This is a very interesting problem, and I will relate this problem to other imaging problems soon. For instance, image deblurring. In image deblurring, you know the kernel, but you don't know the image, the unblurred image. And the other problem is the blind deconvolution. In blind deconvolution, you know nothing about k and you know nothing about u, and you want to solve the problem. You want to identify both. Here, the difference is that you already have a very good ansatz for k as well as for u. That's what makes the problem somehow solvable. Okay. This I already did this comment. So the farther away the scanner is located, the more blurred the detected signal is. So the harder it becomes to solve the convolution problem. And the illumination of the optical sensor, this is the second constant here in the model for k. This one, it has to do with the hardware. And the problem gets harder if you try to identify this constant as well. So usually this is not part of the problem. So this is the amplitude that I represented here. Okay, this gamma factor here. This we assume to be known. And as usual in real life problems, we get is not the exact data, but the data is corrupted by some noise. And the difference between the noisy and exact data is, if not known, we can estimate it by some noise level, which is known. Okay. Then the problem that I have to solve at the end of the day is this one: to determine a pair of partially known and unknown functions, k and u, such that the convolution between these two is equal to the data given or measured by the scan. Okay. And we assume also that the data has a certain noisy level that is known as well. And of course, the noisy level as well as the distance that appears here inside k, the distance from the object to the scanner, it also influences strongly the solution of the problem. Okay. In our model, we can take a lot of information, a priori information into account. For instance, we have a variable partial knowledge of the point spread function, the convolution kernel. We know that it's exponential, and up to a constant, the variation, we don't know k, but otherwise we do know. That makes life much simpler than if you say k is a L2 function and you know nothing about it. Yeah. And the second fact that it can use in our favor is that u, the barcode itself, is a piecewise constant function. And it has a very special form, okay? It's a one-dimensional function in this case, or this strategy could also be used for two-dimensional problems, okay? So I mentioned that this problem is related, but is not equal to two very famous problems in image analysis, the image deblurring problem and the blind deconvolution problem. Image deblurring, let's say you take a photo, there was a photograph here this morning, he was taking several shots, and you can guess that these photos are out of focus. So what happens? Mathematically, you can describe this process as you take the correct image and you make a convolution with a point spread function, okay? And this point spread function says that the light that should be arriving at a certain part of the sensor inside the camera is now reaching a very small area. And because of that, the image gets blurred. So in this case, you have again a problem like this, modeled by this equation here, but you know the convolution kernel. Okay, so it's much simpler. It becomes a linear problem and a very simple problem to solve. The second very well-known problem and very hard is the blind deconvolution. For instance, again with photography. Tomei likes photography, don't you? Mm-hmm. Yes, he does. So you take a photo, you go to the Formula 1 race, and then the cars are speeding in front of you, and then you take a photo, try to take a photo of the car. You're not a professional, but you have a cell phone with you. So of course, it will get messy, you see nothing. So the thing in this process is that not only the image is blurred, like in the first problem, but also you do not know the convolution kernel. You know, you don't know the point spread function. So you have to determine two things. You have to determine the blurring process, and it may be that maybe you didn't go to Formula 1, but you had a caipirinha. Then when you are going to take a picture, you shake a bit, okay? Then the convolution kernel will be completely different. Depending on the process involved in the process of taking the picture, the convolution kernel can be very different, and the thing that you want to photograph as well. So in this context, you have a very hard problem to solve. It's very nonlinear and very difficult to solve. This is the blind deconvolution. You know that the image that you are seeing is the convolution of a true image with a convolutional kernel, but you neither know the true image nor the convolutional kernel. So this is a very hard problem. Fortunately, we are not in this context here. We are in the context of having partial, or actually have almost complete knowledge about the convolutional kernel, okay? And that's why you call this problem a semi-blind deconvolution problem, okay? Okay, let's skip this. What are the relevant tools for our approach here? So first, I'm going to spend more time talking about the piecewise constant level set ansatz. Just like I talked about the level set, what is the difference between the level set, here on the blackboard, and the piecewise constant level set? So you see that for the level set, we had to buy into our model a projection. And this guy here was not nice, because it was basically not differentiable. I draw it here. So it's a function that jumps from 0 to 1, okay? So when you have to differentiate this composition here, although f is differentiable, h is not. So you have a hard time, and you have to use concepts of generalized derivatives in order to get the gradient method going, just as in the pictures that I showed you before. So the piecewise constant level set is different. It assumes that the object they are looking for is piecewise constant, and you don't have to do any projections in order to get this from the model. Okay, so usually when you look at this, equation, and you want to find approximate solutions, what you do is, well, I want to solve this. Then I do some sort of least square. This is a Tikhonov function from phi. And then I have to add some regularization term. And then usually what is used in the regularization of this thing is the H1 norm of phi, because phi is smooth. And we penalize also with the bounded variation of h from phi in order to enforce the characteristic that we want. Okay. So this, the BV norm has some geometrical interpretations but since I'm not going to talk about this method, I'm going to talk about the other. It does not pay off to waste time with this now. So what is the piecewise constant level set? What is the difference from the previous method? The piecewise constant level set, ansatz, works to represent solutions to any kind of problems which are piecewise constant. So we assume that the function, the unknown function, takes two values, C1 and C2. And then we define functions phi1 and phi2, and this projection here. What is the projection? It's C1, phi1 from, this is a level set function, the piecewise constant level set function, and added to C2, phi2 from phi hat. And phi hat is a function that in the domains D1 and D2 take values I minus 1. Oh, you remember D1 and D2 are the domains where U is either 0 or 1. Since in our case the values are 0 and 1, actually this projection here becomes the identity operator because of the simple construction. So U is basically equal to phi hat in this case. We can take C1 equal to 1 and C1 equal to 0 and C2 equal to 1 in 6, or the other way around. Okay. So this representation works in general for any kind of problem, linear or nonlinear, where you know that your solution is piecewise constant. So far I did nothing. No? I just wrote the unknown in a very different way. So, and what we want to do is to solve this convolution equation under the assumption that the level set function, described using this ansatz here, satisfies some constraint. W that appears here is a double L potential. W is defined, we take n, integer n, and define W from phi equals to this product here. So this is a double L. It's a polynomial of degree 2n with multiple zeros in 0 and 1. So if I say that W from phi is 0, it means that phi is either 0 or 1 in the domain that we are analyzing it. Okay, so this is a constraint problem now. Okay, I have the same equation as before, and I add this constraint. So okay, I'm changing difficulties from one side to the other. How do I solve this problem right now? So, and the idea is, okay, let's skip these remarks. I said these things already. The choice of space has to do, I say that phi is in L4n because of the double L. Okay, so usually we take n equal to 1, so phi is in L4 in order to make this approach, which is not very bad. And since we want the operator B is ill-posed, we want to change this Tikhonov functional here in a way that finding a minimizer to this functional here becomes stable. So just as I did in the level set formulation here, I will change the Tikhonov function and add some penalization here, some regularization term. And this regularization term has to do with the H1 penalization of the kernel plus the L4 penalization of the level set function plus the BV penalization of the level set function, because again, I want the level set function to be piecewise constant. But you remember on the blackboard, I had here the BV norm of H from phi. Now I do it directly on phi. I have no nonlinear projection anymore. So things are getting harder because I don't know how to solve this problem using classical tricks, because everything now is nonlinear. The operator is nonlinear, the constraint is nonlinear. So how do I deal with that? This is what these remarks here mean. Usually when you have constraints, you do a Lagrangian approach. You incorporate additional variables, the Lagrange multipliers, and you incorporate the constraint into the original problem. And instead of looking for minimizers, you look for saddle points. The problem is this works very well when you have convexity. If you don't, then you need an additional trick, and that's what we did in this case. Okay. There is a classical book of Rockefeller and Vetz of optimization, probably you know about it, from late 90s, or late 90s or late 80s, where they prove generalized of existence of generalized Lagrange multipliers for problems where the constraint is not convex. And they say that the generalized Lagrange multiplier supports an exact penalty. And the exact penalty in our case is the fact that the function has to be piecewise constant, okay? And our whole job in this work here was to prove that the assumptions of Rockefeller-Wetz were satisfied for this convolution problem. Then we can use a cannon in order to kill this fly here. Not really a fly, maybe a bug. Anyway, so we have our problem here. In order to apply a Rockefeller-Wetz strategy, we must have constraints on all variables, and we have a constraint only on phi. In order to get a constraint on k, we add a slack variable in a very cheap way. And now we have the primal variables kappa, k, and phi. So this is the original constraint, and this is the new constraint, saying basically that the slack variable is equal to the previous variable. Okay, this is a very cheap trick. It's known from methods of multipliers like ADMM. This trick is very well known. In such a way that now you have equality constraints for all primal variables of this problem. Okay. Okay, and what did Rockefeller and Wetz did? They proposed an augmented Lagrangian approach for finding solutions of the constraint optimization problem. And the Lagrangian, you see, this first part here was already present in our problem 10. Then he adds a Lagrange multiplier times the constraints. This lambda here has two parts, lambda 1 and lambda 2, because we have two constraints. And here we have a scalar multiplier that enforces m and w to be 0, okay? This is very interesting. I can make a drawing of this, of the geometrical interpretation of this augmented Lagrangian. You see that we have different multipliers, one in the adjoint space of the previous constraint, and the second multiplier is a scalar. In such a way, and they prove that under certain assumptions, you can find a pair of multipliers, lambda and mi, such that the minimizer of this unconstrained problem here is the same as the minimizer of the original constraint optimization problem. Okay? So, then we come to the duality gap. As I already mentioned to you, this W is not linear. The constraint is not convex. So we may have a duality gap for the problem that we want to solve. So the key idea is to use Rockefeller's strategy in order to construct generalized saddle points for that Lagrangian operator. And use this generalized Lagrange multipliers to construct solutions of the original constraint optimization problem. Where am I? Okay, I'm running out of time. This is a more technical part in order to prove that we have no duality gap under the assumptions that we are using here that are met for this particular problem. So this is the idea of Rockefeller-Wetz, and again, I think I can draw it. Say, if you want to minimize a functional, and you have here, this is the primal and this is the dual problem, okay? If you want to minimize the original problem, because of lack of convexity of the functional to be minimized of the primal problem and the dual problem, you get a duality gap. So the maximum of the primal problem does not coincide with the minimum of the dual problem. The idea of introducing this additional Lagrange multiplier, the scalar part, is that you can change this constraint here. And if the Lagrange multiplier is big enough, what you get is, instead of this level set here, you change the level set. This is the space where you have the dual variables. And then, eventually, you have no longer a duality gap. and you get a saddle point for your problem, for your original problem. And if you know that the augmented multiplier, we call it mu. If for mu, for certain mu bar, you have no longer a duality gap, you can take any mu bigger than this mu bar, because what will happen is that you have sets like this. And once again, for all mu's bigger than a certain threshold, you have no longer duality gaps. And you can find solutions of your primal dual problem. Okay. So this next slides, they relate to this drawing. Basically, we need to define several secondary auxiliary constructions in order to prove, or to be able to characterize the fact that the problem has no duality gaps. And for this problem in particular, for the operator B that we were discussing previously, this property here happens. So this is the generalized Lagrange multiplier. And this is a generalized multiplier that is said to support exact penalty representation. It means it's said to be such that if you find a scalar multiplier big enough, just as I draw it there, then the minimizer of your original problem coincides with the minimizer of the Lagrangian if you take the generalized Lagrange multiplier. So basically, we are changing the minimizers of the original Tikhonov functional by saddle points of a generalized Lagrange functional, okay? And we are able to prove many things for this problem. For instance, existence of generalized Lagrange multipliers. We're able to prove that the original problem attains a minimizer in the set of feasible functions, the primal functions that satisfy the constraint. And moreover, from the inverse problem point of view, we're able to prove convergence. What does it mean? You remember in problem 10, the Lagrangian had a parameter alpha. It's a completely different meaning for alpha than the one we had in Sakis. Alpha is the Tikhonov regularization parameter. So if you have exact data and you construct that Lagrangian functional for different alphas and make alpha goes to 0, you get a sequence of solutions of set of these are the primal components of the saddle point of the Lagrangian functional. These guys here, they do converge to a solution of the problem of the original problem, okay, with no regularization included. And the stability result says that if you have noisy data and the noise level becomes smaller and smaller, then the sequence of solutions that you get, you choose the regularization parameter alpha depending on the noise level, such that delta squared divided by alpha of delta goes to 0. This is exactly the same assumption that you do in Tikhonov theory. What you get is that the solution of the sequence of solutions that you get for each alpha positive, they converge to a solution of the problem with exact data. So these two results here, the stability and the convergence, stability, and semi-convergence results, they are typical results that people in inverse problems aim for. And here, in the last minutes, I can show you the results of this whole process, no? Of using the Lagrangian in order to determine approximate solutions for this problem. So you see, we work in our numerical examples with two levels of noise, 0.5 and 5%. This is the original barcode. We took it from another paper from Ezedoglu that also tried another strategy to do the deblurring process. So this is the signal that you get from the barcode detector. And you have to translate the signal again into the signal here. So this is the information that you get. The blue line is the exact barcode, and the disrupted line here corresponds to your measurement. Okay. And again, we don't know the distance from the code to the detector, and we don't know the barcode as well. So we have to identify two things. So here you see the results that you get from our method. So this is the solution for comparison. And we tried the problem with three different values for sigma. 0.24, 0.26, and 0.28. This means that we are getting, as we go down, we are getting farther away from the solution. So this is already the reconstruction. And you see, if you look carefully, especially at the spots here of the solution, the reconstructed solution, that when you get too far from the object, from the detector, you see that the reconstruction of these lines here get worse. The same thing with this bar here. It gets recognized, but the identification is not perfect, as it was when sigma was small. And this is the scenario when we had small noise level. If we have 5% noise, in this case, you see that this single bar here, this black bar, splits into two bars. So when the noise level is big, or when the distance is big, if we try here instead of 0.28, if we try with 0.30, for instance, then what happens is you start losing bars, or getting extra bars, what that should be known.
Would this be read correctly? I mean, is this going to be translated into a number or a text?
Oh, you have a dictionary. Once you have the code, the translation of the code into alphanumeric sequence, this is done by a dictionary in a very straightforward way.
Yeah.
This is well posed.
My question is, wouldn't it read correctly? Because it looks very good.
It looks good, but maybe it will not. This is the problem. This is why when you go to the supermarket, you have to dance around the reader, because instead of identifying this, you are identifying this. And this extra line here.
If that's not the problem you're working with.
It depends. Maybe here not. Maybe with 5. I think 5% is the limit that we can accept as a solution for the problem. But I tried also with 10%. Then I think I will get an answer to your question. What happens with 10%? Then you see here the exact barcode, and you see that this line here diminishes a lot. And you see that this bar here you have 4 lines. No? Here, basically, you can see only 3. And here is when you have high level of noise and you are far away from the detector. Then you start seeing the problems here. Okay, these two bars here merged into one bar, and this bar is not well defined. It splits in several ones.
So why don't you read the alphabet number directly?
You can ask the people that designed the barcode. I think it.
You know, like, why don't you read the numbers in the letters?
It's also a way of compressing information. When you put the barcode, not only the distance and the number of bars, I don't know much about it. I know that it's a way to put a big number, ISBN number, a big number, and compress it with very few bars. Okay, and if you pick a QR code, you can put much more information than only this. When you go to your airline, you show this ticket, they scan the ticket, they know your name, they know your flight, where you're sitting, they know a lot of things, the air company, and so on. Okay,
yeah, but in this case,
it's a way of encrypting information.
yeah, like if you read the letters, you can create a dictionary.
Yes.
And then you do some comparison, like a Weierstrass measure.
There's a second step that you can do. So if you cannot get a readable code, you can try to find a best approximation. What would be the best sequence of letters and numbers that would match this code? So this is a secondary problem. So most of the times that we have difficulties fighting against the machine in the supermarket is because the distance is not correct. This machine is prepared to work with sigmas within a certain range, and this range is not big, as you can see from here. So if you try to close, you will not get it read. If you try too far, you will not get it read again. So you have, and the supermarket don't have only one line of laser. They have several lines in different directions to try to make the process simpler for the user. Okay, but from the mathematical point of view, this is just a variation of this problem here. So let me finish. I'm almost done. This is the evolution of the method. So we start with an initial guess, which is almost black. And after one step of our iterative method, we use a primal dual method. I didn't talk about the method because it would be another talk. after one step of our primal dual method, we get this approximation. And after 2 steps, 3 steps, after 3 or 5 steps, we have already a very good approximation. So, and it becomes stationary after, say, 70 steps. This is the favorable scenario when you have a small noisy level. And the distance from the code to the gadget was also favorable, 0.25. Okay. With 5%, you see, the more you pose the problem is, the less steps you give in order to make the best you can. So if you have a large large noisy level, you don't have to give too much steps with your iterative method in order to get the best approximation that you can do in this scenario. What else? This is it. Thank you very much.
Probably this codes have some error checking things like the number.
Yes, yes.
Can you use this information to say, well, the solution is garbage, I'm throwing this out?
Yeah, I didn't enter the details of the design of the barcodes itself. There are some barcodes where the width of the white and black bars, they are predefined. So they are multiples of some length. So if you get very far, if you deviate too much from this pattern, then yeah, you know there is something wrong and you can correct it. So there are other tricks.
Use that in your method, put in another restriction somehow.
Yes.
Well,
yes.
it's a class of solutions that.
Yes. Well, as I mentioned in the beginning, the more you know about the solution of the problem, the better you can design a method for finding the solution. If I know, I'm looking for a guy in this audience, there are many guys. So he's a man, he's wearing red, so now I got only one candidate, you know? Yes. No, but this is pink. This is noise. This is noise.
I was thinking when I was taking a look at the presentation. Every time when I take a look at a QR code, every time I take a look at a barcode, I think maybe there is a possibility of reading the same thing 2 times. Because I don't know if the analyzer or the reader is possible to be read 2 times.
Yeah, actually, in the supermarket, they read it many times. When you go to any place that you have to read a barcode, you see that there is not only one line. There are several parallel lines, and they have usually 3 different angles. One horizontal, one to the left, one to the right. So they have several different readings of the same barcode, and they somehow use some kind of strategy to choose which one of this is the better one, or they make some sort of average between these different readings. There are different strategies behind this. That's why there are, I learned that from that site that I mentioned in the first slides. There are barcodes that are easier to read because of these strategies of using bars of specific length. It makes the reconstruction process simpler. And the thing is, if you have a sequence of, I don't know, 10, 12 digits, and you have to read the 12 digits, this is hard. If you have a sequence of a binary sequence, by the way. If you have a large bar, black bar, it means that you have several ones. Or if you have a tiny bar, black bar, it means that you have only one digit, one. So this is basically a binary digit that you have to identify. So and you have to do it. You have to do this processing. Hundreds of. Look at Amazon. So they have this things that go through I don't know, they run automatically in front of the reader, and the reader knows exactly which merchandise is what and where it has to go. The same thing at the airport. When you put your luggage at the airport, they glue something on your luggage, and the rest of the process is completely automatic. Nobody says where your luggage has to go. The detectors turn it around and move it to your plane. No, I think because of that, the barcode process is so much used in our society nowadays because of this automation process and the facility that you have to encode and decode the signals.
I believe so that there is a finite number of products that can be associated with the barcodes.
Most probably, yes.
And also I was thinking, if in the future we use like a 3D image, like creating a height for this barcode, would it increase? And there is research on this topic?
No, the 2D barcodes are already very effective.
Really?
So the best barcodes are not the QR codes that we use it to see. They are simpler to read with the scanner that we have in our cell phones, but they are not the most efficient codes to be translated. Okay, then it becomes a question of the hardware. If you have a specific, I showed you in the beginning a list of several different types of codes. Here, each one of them has a different meaning. They encode letters and numbers in a different way. So, so if you have a specific, this is the QR. No? So if you have one that everybody here has a cell phone, and if this one works better with cell phones, so let's use this one. So, even if this one is easier to read and easier to encode and decode, but you're going to use it, you have your utility function has another parameter inside.
It is enough, even for Amazon, for example?
Yes, of course. If you buy something in Amazon, you get the right thing delivered, so it works.
Now, your numerical method is like you start with the initial guess, and then you get this.
Yeah.
If you
So
get the initial guess.
for our luck, the thing is, once you we have several things that we can use in our favor that I didn't mention. So if you want to close the duality gap, you have to choose that Lagrange multiplier a big number. So you start with initial guess big. Like you did, you do some sort of pre-processing in order to see which are the values that are most favorable. And you start your method with a value as close as possible to the one that you want to find, that you know to be the true range of the Lagrange multipliers. And
But if you put infinity, for the conditions,
then you close study, then this parabola will look like, I don't know. Parabola. You get something like this. Then the problem of finding the saddle point will become harder. No? Because your gradients will be too high. So, and the thing is, once you close the duality gap, you saw you have two Lagrange multipliers, lambda, the traditional Lagrange multiplier, and mu, which is a scalar. And if you have a constraint, the Lagrange multiplier usually multiplies the constraint, so that the level lines become somehow parallel when they touch, like here. No? The second Lagrange multiplier is a scalar that multiplies the norm of the constraint in such a way that you have this effect here. You close the duality gap. And this not always happens. You must have a series of conditions that I avoid talking about here, but they do work in this context. And for our luck, you know that if you find a mu that close the duality gap, any mu bigger than this one will also do the job. So this is not very bad. This primal dual methods like ADMM that I mentioned here, you do a minimization problem in the direction of the primal variables. So you select the Lagrange multipliers, take out of your head. So this is it. And then you solve a minimization problem. Once you get close to the minimum, you stop this process and you do a gradient step with respect to dual variables. It's not a method, it's just one iteration, one gradient step. And then you stop, you take the new Lagrange multipliers and you solve another minimization problem for the primal variables. These 71 steps here are not really 71 steps, 71 dual steps. One gradient step plus one minimization. But because of the structure of the problem, all these things are very fast. We could solve it in a laptop. And the code is binary, so there are several things that makes life simpler from the numerical point of view. Especially because I didn't have to do it. I had a student, a very competent one, that did all the job. So for me, it was very simple.
Okay, let's try.